Assalamualaikum warahmatullahi wabarakatuh. And hi everyone. So we continue our discussion for the subject control system engineering. In previous lecture, we have discussed about how to plot the board plot and how to analyze the performance of the system based on that board plot. So in this chapter, we will continue on how to design controller via this frequency response technique. So before we go further about this topic, let us look at learning outcome of this topic. So at the end of this chapter, you should be familiar with transient response via gain adjustment, lead compensator design, lead compensator design, and combination of lead and lag compensator design. When we talk about design, so the aim that we want to achieve is the system should be stable and the transient response for the system should be follow the requirement. So for stability and transient response design via gain adjustment, so this can be performed by assuming the relationship between phase margin and damping. So recall that the phase margin is closely related to the damping ratio of the system. In previous technique, so we use root locus to find the stability and transient response of the system, where we look at the parameter like TS, TP, settling time, peak time, overshoot, steady state error and so on. So but for this analysis and by using this frequency domain technique, we can relate on how to design via gain adjustment by refer to this phase margin, because from this phase margin we can calculate a damping ratio. The next, for transient response designs via cascade composition, phase margin is related to percentage of overshoot, and because from phase margin that we get from board plot, so we can calculate the damping ratio. So from that damping ratio, we can obtain the value for overshoot. And bandwidth is related to both damping ratio and settling time. And based on bandwidth that we get from the board plot, so we can find this parameter, which is damping ratio and settling time. By reshaping the open loop transfer functions, frequency response to meet both requirements lead to several trials. In this case, we have to reshaping the open loop transfer function frequency response to meet both requirement, damping ratio and the cycle time requirement for this stability and also for this transient performance. Okay, for steady state error design via cascade composition, so its ability to design derivative composition to speed up the system and at the same time achieve the desired steady state error requirement. So in this case, by using this frequency domain technique, we will use lead compensator to perform the same task like derivative composition PD controller. Okay, when we talk about board plot, there are several situations that we have to know. So an open loop system is stable in closed loop if the open loop magnitude plot has a gain of less than 0 dB at the phase of 180 degree. This is referred to the value for gain margin. So if gain margin that we get from the board plot is positive value, that means the system stable. Okay, overshoot is reduced by increasing the phase margin. Based on board plot that we have draw, so we can analyze the performance of the system in terms of overshoot. And in order to reduce the overshoot, so we can increase the phase margin. Next, for speed, in order to improve the speed, we can increase the bandwidth. By increasing this bandwidth, this speed also increase. For steady state is improved by increasing the low frequency magnitude response. Let us look at transient response via gain adjustment. And this one is referred to magnitude response, and this one referred to phase response. Okay, the relationship between damping ratio equivalently the percentage overshoot, like I mentioned just now. Based on this formula, and this is formula for phase margin. Phase margin is equal to inverse tangent to zeta divided by Z negative 2 zeta square plus third 1 plus 4 times zeta power of 4. Okay, from this equation, so confirm that the information that we get from gain margin, we can relate with the damping ratio, because based on this equation, there is value of zeta inside this equation. Okay, by varying the phase margin, the percentage of overshoot is changed. If we want the phase margin of CD, and this one, we have to rise magnitude curve of AB. Point B now at 0 dB. So that means we have to move this to 0 dB. Okay, from this location to this location. So this is what we can do to improve the system by gain adjustment. When we change this fee, so this value also change. Okay, this is the procedure how we can design this transient response via gain adjustment. So first we have draw the both magnitude and phase plot for a convenient value of gain. Second, determine the required phase margin from the percent overshoot. Third, find the frequency omega phase margin on the phase diagram that yet the desired phase margin CD. And CD means we refer to this one. Procedure number 4, change the gain by an amount AB to force magnitude curve to go through 0 dB at omega PM. Okay, the amount of gain adjustment is the additional gain needed to produce the required phase margin. Okay, let us look at this example. For the position control system as shown in this figure, find the value of preamplifier, this one K, to yield a 9.5% overshoot of the transient response for a step input. Use frequency response method and let K equal to 3.6. Okay, to solve this, so first we have to combine all these block diagram until we get only one transfer function. So after we combine all this, we get GSS equal to K times 100 divided by S times S plus 100 times S plus 36. We change all this S with J omega. So the equation become like this. And then from here, we have to do the same procedure like before. So we have to make sure this part equal to 1 like this. And then when we put this one equal to 1, so we have to make sure we multiply this component with 100. And also if we put this one is equal to 1, so we have to multiply this component with 36 like this. So after we rearrange this equation, we get the exact value of the K, which is equal to 100K divided by 100 times 36, or K divided by 36. Okay, so let's choose K equal to 3.6 and the K given by the question. So then the transfer function become 0.1 divided by J omega times J omega divided by 100 plus 1 times J omega divided by 36 plus 1. So in order to find the phase margin, based on this value of overshoot 9.5%, so we can find the desired phase margin by using this equation, which is equal to inverse tangent 2 zeta divided by sec negative 2 zeta square plus sec 1 plus 4 times zeta power of 4. So in order to use these equations, first we have to find this zeta. So the value of zeta can be found by using this formula. This is the same formula that we have discussed in the previous technique, which is time domain technique. Based on this percentage of overshoot, so we just put inside this formula. So we get this zeta equal to 0.6. So from there, and we just put this value inside this equation. So we get the desired phase margin will be 59.2 degree. So from there, so in order to find the desired phase margin, we have to draw the magnitude plot and phase plot. So based on magnitude and phase plot, the value of desired phase margin that refer to this equation is around 13 radian per second. So how we can get this value? Okay, this is come from this calculation where from this both magnitude and phase in order to find phase margin. So we have to refer the distance from this phase plot with this negative 180 degree. Yeah, that's why we apply this formula negative 180 degree plus 59 and this value 0.2%, which is equal to negative 120.8 degree. So which is referred to this value. So this one is negative 19 and this one is negative 80. So negative 20 is somewhere here. So that's why this is the point that refer to this phase margin 59.2 degree. So based on this phase margin frequency 13 radian per second, we can find the value of K. So how? So from both plot and from this both plot, the magnitude at 13 radian per second is found to be negative 42 dB. As you can see here, this is 0, this is negative 40. So this one is around negative 42 dB. So the magnitude plot was drawn for K equal to 3.6. So that we get this both magnitude and phase plot. Okay, therefore we need to bring the magnitude and this one up to 42 dB and up to here and to get the desired phase margin 59.2 degree at frequency 13 radian per second. So we can calculate the new value of K by using this equation, which is K equal to 3.6 and 3.6 because of the initial setting is 3.6. So we just put 3.6 here. Divide by NT log negative 42 divided by 20. So this is to bring magnitude plot up to here. Until this plot, until this both magnitude cross this 0 dB. So from this calculation, we get this value of K is equal to 453.21. Therefore, this K would get the required phase margin for 9.5% overshoot. So the new transfer function become GS equal to 453.21 times 100 divided by S times S plus 36 times S plus 100. So the asymptotic board plot for K equal to 453.21 become like this. Okay? We just move this magnitude plot till this point meet this cross point at 0 dB like this. Okay, now we go to the next compensator, which is lag composition. So the objective of this lag composition is to improve steady state error without appreciably affecting the transient response. So that's mean we want to make sure the steady state error become minimum, close to 0, and at the same time the transient response of the system remain has a previous performance. So this can be obtained by improve the static error constant by maintaining the low frequency gain and reducing high frequency gain without resulting instability. And second, increase the phase margin of the system to your desired transient response. Okay, the transfer function for the lag compensator that we can use to design this kind of compensator is G lag of S equal to 1 over alpha times with S plus 1 over T divided by S plus 1 over alpha T. Same like in previous method, in time domain method, we also use the same transfer function for lag compensator, which is 1 over alpha is represent K, and this one is represent zeros, and this one is represent pole. Now, in order to design lag compensator, so we have to put one zeros and one pole with certain value of K. Okay, to design this kind of controller, so we can follow this procedure. So first set the gain k to the value that satisfies the steady state error specification and plot the both magnitude and phase diagram for this value of gain. Second, the phase margin and the gain margin of the uncomposite system are read from the Bode diagram. Based on uncomposite system, we find the magnitude and phase plot, and from there we can find the gain margin and phase margin. That is a second step. Next step, find the frequency where the phase margin is 5 to 12 degree greater than the phase margin that yields the desired transient response. Okay, next, procedure number 4, select a LED compensator whose magnitude response yields a composite Bode magnitude diagram that goes through 0 dB at frequency on in step 2. Okay, and next, reset the system gain K to compensate for any attenuation in the lag network in order to keep the static error constant the same as that found in step 1. A lag compensator utilize the attenuation of controller at high frequency. So that is to move the gain crossover frequency to a lower frequency while keeping the phase curve of the Bode plot relatively unchanged at the gain crossover frequency as shown in this figure. This one is referred to uncompensated magnitude plot. This one is referred to uncompensated phase plot. This is the lag compensator that we designed based on this transfer function. So when we combine this lag compensator and this magnitude plot for uncompensated system, so the result become like this. And also same for this phase. And for based on this transfer function for this lag compensator, so the lag compensator become like this. And then when we combine this one with the uncompensated system, so the result become like this. This one is phase plot for system with compensator, with this lag compensator. That is the idea how we can design the lag compensator and apply to this frequency domain technique. Okay, let us look at this example about this lag compensator. So given the system as shown in figure Q2, which is referred to the same figure as in example 1, and this one, use Bode plot to design a lag compensator to a 10-fold improvement, 10 times improvement in steady state error over the gain compensated system while keeping the percentage of overshoot at 9.5%. So based on this question, we have to design a controller to improve the steady state error 10 times without affecting the overshoot. So that means the overshoot is remain at 9.5%. So to solve this problem, so first we have to find the transfer function for the uncompensated system without compensator. So where the transfer function is gs equal to k times 100 divided by s times s plus 36 times s plus 100, and same like the previous example. Because we want to improve the steady state error, so we have to find the static error constant. So in this case, we use kv because this is system type 1. So if system is system type 0, so we will use kp. So if system is system type 2, so we will use ka. So in this case, system type 1, because there is one pole at the origin, so that's why we use kv. So kv, we just recall back what you have learned in control 1 in last semester, right? Where kv is equal to limit s gs. So that's why we just put this gs inside this equation, and then we just change all s in this equation with 0. Okay, so after we put all this s equal to 0, so in order to remain the overshoot at 9.5%, so we put this k equal to 453.21, like what we have calculated in the previous example. So after we put in this equation k, and then the result become 45321 divided by 3600. So this is we consider as a old value for KV. For new value for KV, so the improvement is 10%. So based on this ratio, KV new over KV old, the factor is equal to 10, and because 10% improvement. So from here and from this relationship, so we can find the value for KV new. So KV new is KV old at this value time with 10, and then we get the result become 45321 divided by 360. So after we get this K we knew, so we have to find again the value of K when improvement have been done. So in order to obtain that value of K, so we have to use again the formula for KV. So KV new is equal to limit S to 0 SK times 100 divided by S times S plus 36 times S plus 100, where we put all S here with 0. In this case, we have to find the value of K. So this K we knew is already calculated here. So we just put the result in this equation like this. And then from there, we can calculate the value of K. So this is the new value of K. If we want the output, steady state error is improved 10 times. This is only valid for system type 1. Therefore, the new transfer function that yield a tenfold improvement in steady state error is GS equal to 4532.1 times with 100 and divide by this denominator. And next, after we get this value of K, we can draw the uncompensated magnitude and phase plot and using this transfer function. The shape of magnitude and phase plot are same as in question 1, but the magnitude plot is increased for several dB because the value of K is varied. Let us look at how much the magnitude plot was increased. Based on this GS, so the gain for this GS is this value divided by this 36 times 100. Okay, so after we calculate and then we find in dB 20 log K, so we get 42 dB. So this occurs at omega equal to 1 radian per second. So for desired phase margin, this value can be obtained same like in question number 1. So we just use the same formula. We use this formula. In order to use this formula, so we have to find this zeta. So based on this zeta, after we calculate, we get phase margin is equal to 59.2 degree. We have to increase this value of phase margin 59.2 degree by 10 degree, and the desired phase margin become 69.2 degree. So this is we refer to the procedure, and this one the procedure number 3, where we have to add the phase margin with 5 to 12 degree. So in this case, we choose 10. So you also can choose 5, 7, so on, as long as the value is between 5 to 12. Next, after we get this phase margin, so we have to plot this phase margin on the work plot. So after we plot, we get this gain margin occurs at 10 radian per second. At this 10 radian per second, the magnitude plot is plus 23 dB. So if we plot in the work plot, so thus the lag compensator must provide negative 23 dB attenuation at 10 radian per second. This is because we want to make sure this plot should be crossed at 0 dB. Same like what I have mentioned in the previous example. Okay. So after we get all this, so we can design the lag compensator. First step, we have to draw the high frequency, which is we call 1 over T. First, we have to draw the high frequency asymptote that we call 1 over T, which is occurs at negative 23 dB at frequency of 1 radian per second. So we can select about 1 decade below the phase margin frequency 10 radian per second. So 1 decade below, so that means we just divide this with 10. So that means the asymptote occurs at 1 radian per second. Okay, next step, draw a negative 20 dB per decade line until 0 dB is reached. Start at intersection of 1 radian per second. This is referred to this example. So after we get this high frequency 1 over t, in our case is at 1 radian per second. So we just decrease this one to here. The slope should be negative 20 dB until cut at this 0 dB. So this 0 dB we call 1 over alpha t. 1 over alpha t, which is known as a low frequency. So after we do that, so we found this 1 over alpha t is at 0.07 radian per second. From the value of 1 over alpha t and this value 1 over t, so we can get the value of 1 over alpha. From here, we get this value is equal to 0.01 because this 1 over t is equal to 1. And also, so after we got all this value, the transformation for lag compensator is 0.07, which is represent this 1 over alpha times with s plus 1, and 1 is represent this 1 over t divided by s plus 0.07, which is represent of this 1 over alpha t. So from this transfer function for lag compensator, so we can draw this magnitude plot for this compensator where the cutoff frequency based on this equation is equal to 0.07 is somewhere here and 0.07. And if you look at this in this scale, so this is 0.1, so 0.07 is below than 0.1, and then this slope should be negative 20 dB, okay, till 1 over t. 1 over t in this case is equal to 1. So this one refer to this 1 radian per second. Next, after we combine this system with the compensator, so the result for asymptotic mode plot for magnitude plot become like this, and for phase plot become like this. That's all for today. So for lead compensator, we will continue in the next lecture. So try to understand and try to do exercise, and if you still not understand, you can discuss with your friend, and if I still not understand, you can WhatsApp me. Assalamualaikum warahmatullahi wabarakatuh. Thank you.